Swayam Prabha. Digital India. Educated India.
We will now consider an example with multiple sources switching at different times. Fundamentally no different from any case we have discussed before, but just a little more bookkeeping involved. Okay. As always, a circuit with a single capacitor, and let's say this is 1 nanofarad, and these resistors are 2 kilo ohms, 2 kilo ohms and 1 kilo ohm, and I also have a current source. Let's say it's given that Vs switches from 0 to 10 volts at t equals 0, and Is switches from 0 to 10 milliamps at t equals 2 microseconds. Okay. So if I had to sketch these, this would be Vs. The x-axis is of course time, and the y-axis is either voltage or current, and Is would go from 0 to 10 milliamp at t equals 2 microseconds. Okay. So looks slightly more complicated, but essentially between the terminals of the capacitor 1 prime, we can still represent the whole thing with a single source in series with a single resistor, or a single current source in parallel with a single resistor. Okay. So either can be used. I will use the Thevenin equivalent here, but you can use the Norton equivalent and verify that the answers are exactly the same. Okay. So let me call these Vs and Is. Let me keep them as variables for now, and 1 prime, then this is what I have. Okay. So now again I will not show the details of calculating the Thevenin equivalent voltage, right, that you can do quite easily, and you will see that the voltage between 1 prime when it's open circuited, in other words the Thevenin voltage will come out to be Vs divided by 2 minus Is times 1 kilo ohm. Okay. So that's what it is going to be. So now if you evaluate this, Vs is changing at some time, Is is changing at some other time. Okay. Is is like that. So if you sketch this entire input to the circuit, right, so if I calculate Vth in series with Rth, and I have my capacitor there which is 1 nanofarad, and if I sketch this Vth, it will look like that. So this is really all I need to do. Okay. So Vth will be 0 before t equal to 0, because both Vs and Is are 0. All you have to do is to substitute these values into that expression, and between t equals 0 and t equals 2 microseconds, the output will step up to 5 volts, which is Vs by 2, and Is is still 0. Okay. And after t equals 2 microseconds, the contribution of Vs will be 5 volts, it's Vs by 2, and contribution of Is will be minus 10 volts. Okay. So what happens is this will switch down and stay at minus 5 volts forever. Okay, because we have no other changes that are specified. So all we have to do is still solve the same circuit. By the way, the value of Rth between these two terminals, again calculate it for yourselves and see that it comes out to be 2 kilo ohms. So all we have to do is still solve the same kind of circuit as before, but with a slightly more exotic input. Okay. as long as the inputs are piecewise constant, this is quite easy. You treat each piece separately as a separate step input with its own initial condition. Okay. So first we have this step, the input steps from 0 to 5 volts. Okay, and let me say that the initial condition just before the first step is applied at 0 minus is 0. It can be anything, but let me assume that it is 0. So then for this part of the curve from t equals 0 to t equals 2 microsecond, essentially I have only a single step input which goes from 0 to 5 volts. Okay, that is, I will be solving the circuit for an input like this. After this it will change, but it doesn't matter, its effect will only come later. This is 0 volts, that is 5 volts, that is 2 microseconds. And we know how to do this, we have done this already. So the solution from t of 0 to 2 microseconds will be, we can still use the general form, which is Vc of infinity plus Vc of 0 minus Vc of infinity, the whole thing times exponential minus t by Rc, and Rc here you can see is 2 microseconds. Okay. So what the output will do is this Vc of infinity is 5 volts as far as this step is concerned. Okay, we are only solving with this step input. That's the one thing you shouldn't get confused about. It's not that Vc of infinity will actually reach 5 volts because the input is being changed again. Okay, but if this were the step, if this 5 volt step were persistent till t equals infinity, it would go to 5 volts. Okay, so it's the final condition assuming only this step is applied. That is an important thing to understand. So Vc of infinity here is 5 volts. Okay, plus Vc of 0 is 0 and we have minus 5. So essentially I have 5 volts minus 5 volts exponential minus t by 2 microseconds. And if I sketch that part, it will do something like that, and it would eventually have reached 5 volts. Okay, but at t equals 2 microsecond we have the other step. Okay, so we can treat that as a separate step, and that step is going towards minus 5 volt. Okay, so for the following time period, 2 microsecond to infinity, because we have no other changes till infinity, so this will be valid, and this is a different step response. And as far as this step is concerned, see, the input is going to minus 5 volts, and at t equals infinity the capacitor will be an open, so whatever Vth is, that will be the value of Vc. So as far as the second step is concerned, Vc of infinity is minus 5 volts. Okay, plus Vc of 0 for this is the initial condition. Initial condition is just before the step. Okay, I don't want to make the arguments too complicated by writing 2 microseconds and all of those things. I am showing this with a combination of sketches and pointing out what happens where. So this Vc of 0, don't assume it's t equals 0 here, it's the initial condition for whatever step is being applied. So it is at 2 microsecond. So if you calculate it, the first step, the 0 to 5 volt step, will cause a change like this, and it turns out that this, again you calculate for yourself, this is done by substituting t equals 2 microseconds in this equation, and it turns out to be 3.16 volts. Okay, so Vc of 0 for the second part of the response is 3.16 volts minus Vc of infinity. Okay, and that Vc of infinity is nothing but minus 5 volts. Okay, because that's where it's eventually going to reach, and the exponential is exactly the same because the circuit is the same and the time constant is the same. Okay, so essentially each time the change happens, you treat that as a new step, the initialization of a new step, and solve for it. So for this part, the solution is minus 5 volts plus 8.16 volts exponential minus t by 2 microseconds. So what it will do is the following. So it will eventually reach minus 5 volts. It's supposed to reach that. The way it will do it is like that. Okay. So the first step will take it to some positive value. It doesn't reach all the way to 5 volts because we have only given 2 microseconds for it, and 2 microseconds is the time constant of the circuit. It takes many time constants for it to reach very close to 5 volts. So now it reaches this voltage, and then from there it falls back to minus 5 volts because of the application of the second step. Now one thing I have to be careful about here is this T should be really T minus 2 microsecond. I have not been very strict with notation here. This T does not refer to the time axis T here, but it's the time elapsed after the second step is applied. Okay. So maybe I should have written T minus 2 microsecond over there. Okay, because this applies only to T more than 2 microseconds. So this is the second part, and this is the first part. Okay. So in a similar way, you could have a network with many resistors, many independent sources whose values are stepping from one constant to another, or you could have fixed voltages and currents with some switches being operated. When you change the states of switches, what can happen is that it can effectively look like a step input, and sometimes when you change the states of switches, even the time constants can change. Okay. So you have to be aware of all of these things, but after each step is applied, you treat it as a constant input circuit with certain initial condition and then work out the result. Now at the time of the next step is applied, you calculate the initial condition from the previous solution and proceed. Okay. So even if you have a very large number of steps, you can do it systematically. You can solve for the voltages or currents in the circuit systematically like this. Okay.